Now, this is a pulse of light, the fastest thing in the universe, slowed down so drastically that you can actually watch it crawl through a solid glass bottle. Your eyes and the mechanical shutters inside traditional cameras have a strict speed limit. Try to capture any object moving too fast, and the physical mechanism simply cannot keep up, reducing reality to a continuous blur. This animation illustrates the mathematical dilemma you face when trying to fix that blur, the resolution paradox. You can crank up the camera's frame rate, but doing so forces you to eject image quality, ditching pixels to buy speed. This happens because of a physical bottleneck. A camera sensor has to funnel all its visual data down a pipeline. When you attempt to clear that sensor millions of times a second, the data piles up. The pipe physically cannot clear the information fast enough. Because of that readout limit, even a top-tier research camera from 2020 still outputs low-resolution footage at maximum speed. Yet look at this photograph taken back in the 1930s. The motion is sliced into impossibly crisp, sharp layers. To achieve this kind of clarity at speeds that reveal the hidden mechanics of physics, scientists had to stop trying to build better sensors. They had to abandon traditional photography entirely and hack the physical rules of light and time. In the 1920s, electric motors powered a massive wave of industrial manufacturing. But when these machines misfired, the gears spun too rapidly to diagnose the problem by eye, and standard cameras were far too slow to catch anything but a smudge. An MIT engineer named Doc Edgerton realized the flaw wasn't in the camera's shutter. The solution was the light source. He moved his setup into the pitch black. By leaving the camera's shutter permanently open in a dark room, he guaranteed no blurry image could form on the film. Then he built a custom trigger. He forced a high-voltage electrical current into a gas-filled tube, ripping electrons off the atoms to instantly create a burst of 10,000 Kelvin plasma, nearly twice as hot as the surface of the sun. That plasma created a flash lasting just 10 microseconds. By swapping a slow physical mechanical shutter for an ultra-fast pulse of light, Edgerton completely bypassed the data bottleneck. He sacrificed a moving video feed, but gained a single perfectly frozen slice of time. A microsecond flash works for a factory motor, but if you want to capture a sequence of frames showing a laser pulse itself in motion, you need speeds of 1 trillion frames per second. To beat the readout limit at that extreme speed, MIT researchers stripped the camera hardware down to a single hypersensitive pixel. It's essentially a LiDAR sensor designed exclusively to count individual photons. This diagram shows the consequence of that hardware. The single sensor records time flawlessly, but it produces zero spatial imagery. It only generates a raw timeline plotting exactly when those light particles hit it. To build a picture, researchers weaponized repetition. They fire an identical laser pulse into a controlled scene thousands of times. By slightly shifting its aim across a grid with each consecutive flash, the single pixel slowly paints a complete high-resolution environment. Instead of observing an event all at once, they observed thousands of identical micro-delayed repetitions. That is how you bypass the physical limits of a sensor to build a video of light itself. But to watch individual electrons shift around molecules, light is actually too slow. You need an entirely different wavelength, X-rays, and you need them pulsing at attosecond speeds. An attosecond is a fraction of time so small that 1 attosecond is to a single second what 1 second is to the entire age of the universe. Generating that specific, impossible light requires a landscape-altering machine. This is SLAC, a U.S. national lab housing a 3.2-kilometer-long linear particle accelerator. This animation outlines the undulator mechanism inside. Electrons are accelerated to over 99.999% the speed of light and forced through alternating magnetic poles. This makes the electrons wiggle, emitting incredibly sharp, tightly packed bursts of X-ray radiation. Here, scientists combine Edgerton's bright flash with the single pixel's repetition. They use a laser to trigger a reaction in a molecule, then fire the X-ray strobe to capture it. By repeating the exact same reaction with microscopic time delays, they assemble an incredibly precise sequence. Merging an impossibly fast light shutter with endless repetition entirely circumvents the camera hardware limit. The result is a quadrillion frame per second movie of quantum mechanics. In less than a century, we scaled our vision from diagnosing heavy factory motors to mapping the invisible engines of chemistry. These shifting electron densities are the precise physical forces that dictate how every piece of matter bonds together, breaks apart, and behaves during a reaction. For decades, physicists could only understand these interactions by writing complex mathematical expressions and calculating the theoretical outcomes. Now, by breaking past the physical limits of sensors and slicing time down to the attosecond, scientists no longer have to rely solely on theoretical predictions. We can watch the source code of the universe execute in real time.